Today we're going to be looking at a really cool concept in linear algebra called vector spaces. So vector spaces are defined as a collection of objects, or vectors, with defined addition and scalar multiplication such that these 10 properties hold. I know, a lot. But also, as we're considering all these 10 properties, I want you to remember that this is a time where we want our imagination to run wild. We can let our mind be flexible and our imagination active as we try to find some kind of collection of objects that fit these 10 properties. So we can kind of think, just to kind of give you like a little teaser here, our vectors of size n are a vector space. Our matrices of size mn is another vector space. Our continuous functions over an interval I are also a vector space. So now that we have kind of generalized one whole set of objects, we can kind of break it into little pieces as well. So we call these subspaces. So a subspace, we can kind of think of this like the United States of America. So we take the United States, it's this whole collection of objects, a bunch of different states, but they all have some unifying properties. But when we break it into our different states that have their own set of rules, own set of characteristics, so like for example, Wisconsin, known for being a cheese state, that is a subspace of our vector space of the United States of America. So Wisconsin is its own subspace because it has its own rules, but it also still follows all of the rules of the United States of America. So our subspaces, the definition is that we have a subset of our vector space, and we're going to call it S, and it has these properties such that the zero vector is in this subset. If we take any two elements in this subset, we add them together, that's also going to be in our subset. So it is closed under addition. And lastly, we have, if we take a scalar and multiply it by any vector within the subspace, we are going to see that that is also in our subspace. So that's what we make our subspace out of. So now let's look at a few examples. We're going to go ahead and erase this, but keep these in the back of your mind because they're going to be really helpful for analyzing different collections of objects. Let's consider our first subset. Our first subset, we're going to call it S1, is just simply going to be the zero vector. Okay, so let's see, is this a subspace? We know that it is a subset of our vector space because the vector space has a condition that the zero vector must be in it. So we know that it is a subset of our vector space. And then our first condition here, is the zero vector in our subset here? Well, it's kind of defined as that, so we know that our zero vector is in our subspace, so check. For our second condition, if we take any two vectors in our subset, are we going to get their sum in the subset? Well, since we only have one element in our subset, if we take our zero vector plus our zero vector, what are we going to get out? Oh, our zero vector. And that means that our zero vector is in our subset. Check. By the way, we are looking at the vector space of Rn. Any vector space of real numbers, so we have our zero vector in there. Okay. And now if we look at our third condition, if we take some constant c, it's a real number, and multiply it by any element in our subset, since we only have one, we can just use our zero vector. That's going to equal our zero vector. And is the zero vector in our subset? Yes. So we know that we've just met all three conditions of a subspace. So we know the S1 is a subspace. I think probably in all of these conditions you're thinking, well, yeah, obviously, that's kind of like trivial. So we call this a trivial subspace. So let's look at a non-trivial subspace. So now for our second subset that we're going to be looking at, we're going to be looking at the subset of R3 such that we have a triple of x, y, and z, such that z is equal to 2x plus 2y. Okay, so let's see if it meets all of our conditions of a subspace. It's obvious that it is a subset of our vector space, so let's just check to see, is the zero vector in there? Okay, so if we let x equal y equals 0, we will see that 2 times 0 plus 2 times 0 equals z. So then we know that 0, 0, 0 is in our subspace. So check. Now if we take our second one, let's write this like it looks like a matrix, just so it's kind of easy for y'all to visualize. We'll have our x, y, and then we'll do x1, y1, and then 2x1 plus 2y1. We're going to have this vector. We can see that that is in S2. We're going to be adding it to another vector in S2. So x2, y2, and then 2x2 plus 2y2. Their sum is going to be equal to x1 plus x2, y1 plus y2, and then 2x1 plus 2x2 plus 2y1 plus 2y2. So we can simplify this and see that we have x1 plus y, or x2, y1 plus y2, and then 2 times x1 plus x2 plus 2 times y1 plus y2. Whew. So now we see that this is indeed in our S2. So the sum of any two vectors in S2 is also in S2. So now if we look at our third condition here, we want to see if we take some constant and multiply it by any vector in our subspace. We're going to see if this is in there as well. So we're going to see that this is equal to cx1, cy1, and then 2cx1 plus 2cy1. So then we see that cx1 right there, cy1 right there. So then we see that this scalar multiple of this vector in our vector space is in S2. So then we know that this S2 is a subspace because it meets all of our conditions. Also keep in mind that subspaces also have all the properties of a vector space because they are a subset of our vector space. So, okay, now we see S2 is a subspace. Because none of these were very well, yeah, obviously, unless you've been doing this for years and years and years, we call this a non-trivial subspace. Now let's look at one more example of a subset of the vector space. So for our next subset of our vector space, we're going to be looking at, in our vector space R2, the set of vectors xy such that x is always greater than or equal to 0. We're going to represent this graphically. So we have our coordinate plane. We want all of the vectors such that x is greater than 0 or equal to 0. So it's going to be this set right here. Make sure we don't go over the line. So all of this side of the coordinate plane. So coordinates or quadrants 1 and 4. Okay, so now let's think here. If we take a vector in this space and we want to add it to another vector in this space, so we just take this blue vector, put it right there. Are we going to get another vector in this space? Okay, this is going to be this vector right here, that orange one. Oh, then look, that is still in the space. So, and also if we think about this a little bit more abstractly, if we have two numbers that are both greater than or equal to 0, if we add them together, are they ever going to dip below 0? No. So that means that we are closed under addition. And we also know that the 0 vector is in there because it is right there. You can see it, you can touch it, because x can be equal to 0. So we still have this space here. We want to make sure that it's staying in there. So if we take some vector in this subset here, let's take this one right here. And let's say perhaps this is the vector 3, 5. For by third condition here, it says we can take any kind of scalar in our real numbers and multiply it by this vector, and that should still be in our subset. So if we take -1 and multiply 3, 5 by -1, what are we going to get out? Well, we're going to get out -3, -5. So this is in R2, but is it in S3? Is it in our subspace? No, because if we graph this one right here, we're going to have -3, -5, which is going to be like right down here, which is not in our subset. But so because this subset does not satisfy our third condition, even though it satisfies like 67% of our conditions, we can't let it fly. So this is not a subspace. Subspaces are a nice way of us being like, okay, so this is like a tangible subset that we can work with, that we know is going to hold together, hold strong and true while we analyze it. So we just saw an example of a trivial subspace, a non-trivial subspace, and then one that's not a subspace. So now go out and have fun and corral up some subspaces.